Good day. Today we will tell about the laws of crystallography. Here you can see the plan of our lecture. There are the Stennon's law, Wolf's and Bragg's condition, and Hayui law. The first law and the very important law, the Stennon's law. When a crystal grows, the particles are arranged in irregular and symmetric spheres, grids, lattices. It means that the crystal grows in such a way that its faces grow parallel to themselves. You look here, of course it is a scheme. The area of faces, their form, can vary for various reasons, but the mutual inclination of the crystal faces remains unchanged. This is a quantitative law of crystallography opened by Nicholas Stennon in 1669. The name of law is the law of Constancy of Angles. In all crystals of the substance, under identical conditions, the angles between the corresponding faces are constant under the same conditions. Identical conditions mean the temperature and pressure, that is, if the substance has several polymorphs, for example as ferrum or titanium, we talk only about one modification, the same modification. This law implies that the angles between the crystal faces of one substance, despite their outward differences, for example shape, size, and even the number of faces, is always constant. The law of constancy of angles makes it possible to reduce all the variety of form of crystals to a set of angles between faces and to represent them with the help of projections. This law has played a prominent role in the development of crystallography. Before the discovery of X-ray diffractions, all crystals of a matter were characterized and distinguished from each other only by the angles between the faces. At that time, the main method of diagnosis was to measure the angles with the special equipment, a goniometer. Here you can see the scheme of this equipment. The light beam from the source S is reflected from the crystal face K, you can see here, and falls to the telescope O. The angle between the incident and reflected beams is measured on the scale M, located on the rotating limb R or P. Turning the crystal or pipe maybe, one can measure the angles between all the faces. Now these angles are measured using X-ray, and it is sufficient to have not a large crystal with a regular face, but a small grain of the substances. As the wavelengths of X-ray are commensurate with the interatomic distance in the crystalline materials, They are natural diffraction lattice. Here you can see the scheme illustrating the diffraction of X-ray beams, and this scheme allows to understand the Wolf-Bragg condition. The diffracted rays are mutually reinforcing if the path difference between them nabla is a whole number of wavelengths. The other words, n multiplied lambda, where lambda is wavelength, and n is only integers 1, 2, 3, and etc. This figure shows that the path difference between the incident and diffracted rays bathing is nabla, and this equation. S0 is a beam of monochromatic X-rays incident at the angle theta to the family of parallel atomic planes, and S here is a beam of diffracted rays to the base scattered by the two neighboring flat lattices. The whole family of parallel lattices give the maximum intensity. There must be satisfied the basic law of X-ray diffraction, this equation. This equation expresses the Wolf-Bragg condition opened independently by Bragg and Wolf in 1913. In other words, if the beam with wavelength lambda is incident to the set of atomic planes parallel to each other and separated by the distance d, it generates a different beam at angle theta. Thus, flat lattices in the crystal structure, they correspond to the faces of the crystal, under certain angles of incidence can reflect X-ray. These reflections are recorded, the diffraction patterns display the uniform of crystal symmetry and give an opportunity to measure the interplanar distance d, the angles between faces, and etc., and consequently to diagnose the crystalline materials. At present, X-ray analysis based on the Wolf-Bragg law is a fundamental method for studying crystalline phases. Here you can see the last crystallography. The law of integers, the higher or Gauss law. Plane A, B, C may be the face of a crystal only if a specified ratio is true. That is why the growing crystals have faces only of certain inclination, typical for the substances. The faces for which the ratio PQR is irrational are impossible. As a rule, PQR for these numbers don't exceed 5.